everybody has slightly different problems on web work and slightly different numbers. So I'm just going to talk about like the framework of this problem. And the framework of this problem says that we have a population. Insert your favorite critter here, right? So in this case, it's a population of cattle. But, you know, we could replace that with anything. And what we're told is that it's increasing at a rate of, and now, again, this is a place where for this particular problem, people are going to have different functions. But if I just think about this as kind of a general framework, then we're given some kind of function in here. So my function says 100 plus 4t per year. And per year where t is in years. Where t is in years. Now the second part of the part that's like actually the question part says by how much does the population change and for me, it's between the 9th year and the 14th year. So I'm just going to pause here for a second to kind of talk generally about what this is saying here. So we've been given something that is a rate, and then we're being asked about how much the population changes between the 9th year and the 14th year. So there are a couple of different ways that we can conceptualize this problem, but one of the ways that we can do it is by using the units in the problem. So we've got this population that's changing at a rate of 100 plus 4t per year. Well, what does that actually mean units wise? That's telling me that we've got some kind of function here of 100 plus 4t, but the units are cattle per year. So that's how much we're changing by. So if I want to know something about what's happening to the population, I know that I would have to multiply that by years to get myself back to cattle. Now, the other thing that's happening here is I'm looking at the difference between the 9th year and the 14th year. So whatever else is happening, I know that I'm going to be doing some kind of subtraction of what's going on at the 14th year minus what's going on at the 9th year. So we have two options of how to think about this. We can think about this in the 4.6 sort of model, where I know that that's a rate of change. So I could write that as a differential equation, and I could write that as like dn dt. I don't know why we always use n for or not always, but it seems like we often use n for the total population when we're talking about biology. So I'm just going to stick with the n. So that's my rate of change. And now I need to know something. If I knew the function for the number of cattle we had, we could just look at what's the population at the 14th year and subtract off the population at the 9th year, and that would give us the total change. So my first step would be to find that antiderivative so that I would have a population function. So I'm looking at 100t plus, if I find the antiderivative of 4t, I'd have 2t squared. And technically I'd have plus some sort of constant. And I'm going to call that constant, that would be the initial number of cattle. But we don't know enough to figure out what that constant is. Fun fact, doesn't matter, because We only care about how much the population changed between the 14th year and the 9th year. So if I took this approach, I'd then be looking at n of 14 minus n of 9. And if we do that, I'd have 100 times 14 minus 2 times 14 squared plus that constant. And then I'd subtract off 100 times 9 minus 2 times 14 squared plus the, I don't know why I put the 14 in there, sorry, 9 squared plus that constant. And notice those constants are going to cancel out. This would be that like section 4.6 approach. Well, one of the things that Professor Chaudhary was mentioning like right at the beginning of class on Friday is that there are lots of different ways to look at the same thing. And one of the other ways that we can look at this same thing is to say, well, we would have ended up doing exactly these same steps if we just interpreted this as I need to add up a bunch of little changes, and adding that up means we're adding them calculus style with an integral. I need to add up a bunch of little changes times a little change in time. And that gets back to the units thing. So if this has units of cattle per year, then that dt has units of years. Those would cancel out, giving me just total cattle. And since I'm going from year 9 to year 14, this would lead us through exactly the same set of steps here, except we wouldn't bother writing the plus c because we know it was going to cancel out for that definite integral. Do you all want to try this on your own? Or do you just want to see me do it? Any votes for try it on your own? Okay, I got a couple thumbs up for try it on your own. So let's go for that. I'm going to give you, I'll give you like, I don't know, 2 minutes, 3 minutes to try this on your own. that was about 3 minutes. I don't know if that was quite enough time for everybody, but I will maybe go ahead and get started. So if you aren't sure where to start on this, I tried to give some suggestions. Draw a picture, find the intersection points, figure out which function is on top. When I say draw a picture, I'm pretty good at drawing things, but I do have some tips if you're not super comfortable drawing things. When it comes to finding area between curves, the only thing we're trying to figure out is where do they intersect and which function is on top. And I can kind of do both of those without a great picture. Here's what I mean by that. I know that y equals 2x is a line with a positive slope. So even if you don't worry about it being more complicated than that, just think about, I have a line with a positive slope. This is a parabola because I've got the x squared, and it's a concave up parabola because my invisible number in front of the x squared, or that term, is positive. So whatever else is going on, I have a concave up parabola. And now if I come in and I put a line with a positive slope, I know the line is on top. That's it. I didn't have to draw anything fancier than that to know that the line has to be on top and the parabola has to be on the bottom. Now, in order to actually finish off writing our integral, I do need to know what the intersection points are so that I can get the bounds. But partial credit, I already know line is on top minus parabola has to be on the bottom. Now let's go find those intersection points. To find the intersection points, I'm going to set the two functions equal to each other. So I'm looking at 2x is equal to x squared minus 4x. This is a quadratic, so we have options for how to solve it. I'm pretty sure if you are given a quadratic on the test, it's going to be something that factors. He's not expecting you to reach for a calculator and use quadratic formula. It's going to be something that factors. So to factor, I need a 0 on one side of the equation. So I'm going to subtract 2x from both sides to give me 0 is equal to x squared minus 6x. And here I can factor an x out to get that the x values at my intersection points are 0 and 6. And that's it. That's all I need in terms of the picture. I don't need to do anything fancier than that for the picture. Now we're ready to finish off the definite integral. We have two choices here. We can combine things together first and then find the antiderivative, or find the antiderivative of each piece separately. And I'm going to go ahead and simplify that first and say I'm going to have 2x minus a minus. I'm going to get 6x minus x squared. So when I find that antiderivative of 6x, I'm looking at 3x squared minus 1/3 x cubed. And we're taking that from 0 to 6. So if I plug in the 6, I'll have 3 times 6 squared is 36 minus 1/3 of 6 cubed minus plugging in 0, I would get a big fat 0. Could I take the time to simplify this? Absolutely. Do I plan to? No, I do not. But you certainly could simplify that down if you're really great and quick with numbers. Questions about this before we move on to talk a little bit about volumes. I'm not seeing, there we go. Oh yeah, that's a really great question of why does it matter which function is on top? So my short version is the reason that it matters which function is on top is because we want to make sure that we're ending up with a positive answer for the area that's enclosed. And if we think about what's happening in this integral, this piece right here is the height of an arbitrary cross section. And this is the base of that cross section. So when I'm trying to find the area in here and I draw an arbitrary cross section in, then the way that I would find the height of that rectangle is that I would take the y value from the top and subtract the y value from the bottom. And that's how I would get the height. So when we're interpreting this area as height of a cross section times the base of the cross section, that's how we end up with that formula of thinking about a top minus a bottom. So a couple more questions are popping up. One is, do we actually need a picture? No, we do not actually need a picture. We do need to know which function is on top. So there's a suggestion in the chat for another way that we could figure out which function was on top without a picture. And I'm going to squeeze it in. We're going to get this going. So alternately, if I wanted to figure out which function was on top, my other option is to say, okay, we know where the intersection points are. They intersect at 0 and at 6. So if they intersect at 0 and at 6, then I can pick any number between 0 and 6 and plug them into the two functions to figure out which function is bigger than the other. So let's say between 0 and 6, I'm going to keep my life simple and check at x equals 1. Well, if I plug in 1 to our line, that would look like y equals 2 times 1. So that would be at a height of 2. And I'll just label these y1 and y2 for my convenience. And if I look at y2 and we plug in 1, I'd have 1 squared minus 4 times 1. So that's -3. So I now know that the parabola has a lower y value than the line does. So this would also tell me parabola is on the bottom, line is on the top. Just quick with lines, if we're doing a quick sketch, really the only thing we need to know is does it have a positive slope or a negative slope? So if I'm thinking about y equals mx plus b, I'm really just looking at is that m positive or negative? For parabolas, I'm really just thinking about, are they concave down or concave up? And that's like, if I have ax squared plus bx plus c for my parabola, it's really just coming down to what's the value of a? Is a negative or is a positive? For exponential functions, something like y equals e to the kx, here what matters is I'm going to have an increasing exponential if k is greater than 0, and I'm going to have a decreasing exponential if k is less than 0. And I would say that's usually enough to get sort of a fake picture going. So one of the examples that I think I did last week, I don't know, I had something like y equals e to the -3x and something like y equals x minus 12. So my trick for getting a fake picture going. And I call it a fake picture because I'm not worried about it being to scale. And I often don't even put the axes on it, right? So if I have y equals e to the negative 3x, that is some kind of decreasing exponential function. And if I have y equals x minus 12, well, that's some sort of slope, some sort of line with a positive slope. So that's enough to get me a fake picture. By the way, if we do have some sort of exponential and some sort of line, we will be given the bounds for x. So we'll be told that we're looking for the area between the curves, and then we'll be given x values. And with those x values, we'd be able to figure out whether it's sort of this part of the picture or this part of the picture. But if you have an exponential and a line or an exponential and a parabola, you'll be given the bounds or you'll be given a picture. I'm going to imagine that I'm taking this shape and spinning it around the x-axis. If we were in the office, I have all these great visual aids for this section, but I don't have them at home with me, so we're going to fake it. So what we're trying to do is find the volume of the mythical object that would be created if I took that shape and spun it around the x-axis. Here's how we're going to do it. So I'm going to come in here and I'm going to draw my arbitrary cross-section. My arbitrary cross-section, usually a rectangle, because I know how to find the area of that. So there's my arbitrary cross-section. Let's see how I did. Pretty close. It's a little tall. There's my arbitrary cross-section. Now, I said we were going to spin this around the x-axis. So I'm taking my arbitrary cross-section and I'm spinning it around the x-axis. So it's coming out at us. And now you can imagine that I somehow like pushed my finger through the board and I kept spinning that all the way around until it popped back up here again. So this, we spun it around. When we did that, it went in a complete circle. So I took my arbitrary cross-section and it went in a complete circle, but it has a little bit of thickness. So this arbitrary cross-section turns into a cylinder. And the volume of a cylinder is equal to pi r squared times the thickness. We usually call it pi r squared h, but the h is not the best option for us because h to me sounds like height. And really we do mean in terms of this cylinder that it has a little bit of thickness. So my little bit of thickness here is a little bit of dx. Pi is just part of the formula, but that r squared part, if I think about my arbitrary cross-section, that's the thing that was spinning around in a circle. So the radius is really this height of the cross-section. How do I find the height of that cross-section? I look to the curve. So my radius is equal to x cubed because it's telling me at this point, that's the height. Then I add them up calculus style. And in this case, we're taking our cross sections as far to the left as 0 and as far to the right as 2. If you're looking for something to put on that page of notes, this is definitely worth putting on your page of notes. I would say go ahead and just put a practice problem on your page of notes. if we're going to finish this off, then one of the things to note, we want to make sure that we take the function and square it first before we're trying to find the antiderivative. So if I'm taking this to be an actual number, I'll have pi will go from 0 to 2. And when I square x cubed, that's x cubed times another x cubed, and I'll have x to the 6th. Then we can find that antiderivative. So I'll have 1/7 x to the 7th from 0 to 2. Plugging in 2, I'll have 2 to the 7th. Let me get my pi over 7 times 2 to the 7th minus pi over 7 times 0 to the 7th, and walk away. We don't need to simplify that anymore. And let's go from 1 to 5. So I'm imagining this piece right here, and then we're rotating it around the x-axis to form a solid. So if I come in and I draw my arbitrary cross-section, so I'm drawing in an arbitrary rectangle in here. And then think about spinning that rectangle around in a circle. It still has that little bit of thickness, or dx, but that radius is the height of the function at the point where we drew our cross section. And the height of the function is coming from doing x squared plus 1. So our volume equation here would look like pi. We're going to integrate from 1 to 5. We'll have our radius squared piece, but that radius is coming from our function. So x squared plus 1 whole thing dx. Before we find the antiderivative, super important that we square that function out first. So I'm going to have x to the 4th plus 2x squared plus 1 dx. Then we can find our antiderivative and plug in the bounds. So finding my antiderivative here, what's that? 1/5 x to the 5th plus 2/3 x cubed plus an x. And then all of that is going from 1 to 5. Now I gave us pretty messy numbers here, but I've taken a look at the web work. So if we plug those in, I've got 1/5 times 5 to the 5th plus 2/3 times 5 cubed plus 5. And this time I gave us a 1, not a 0. So we actually have to, well, even when it's a 0, you should still at least mentally plug it in. But for sure, I'm going to have to actually plug it in with this 1. So I've got 1/5 times 1 to the 5th plus 2/3 plus 1. Again, if this is the test, walk away. Heck, even if it's web work, I would just type that garbage in and then walk away. Pausing just for a second. So I know where the next, well, I think I know where the next question is headed. If we are doing a rotation, we're only ever going to use this formula. We're only ever going to use essentially a to b pi f of x squared dx. That's all we're dealing with if we're talking volumes of rotation for 17b. But there are other volumes that are contained within section 6.4. So let's talk about the other way we can think about volume. And the reason that we're always going to get this shape is because when we're rotating something, we always have that circle with a little bit of thickness. But what if we're not rotating and instead we're taking slices? I'm going to erase all of this and then we'll do a problem with some slices. I was looking around my room for something fun to slice through. Not actually slice through, but just think about slicing through. I didn't find much, so we're gonna have to fake this. But I do have a box of tissues. So if I wanted to find the volume of this box of tissues, I think we can all agree that the easiest option would be to measure this side, measure this side, measure this side, multiply them together and get the volume. But let's pretend that we really wanted to make life complicated and use some calculus. Well, if I wanted to use some calculus to find the volume of this object, one thing that I could do is imagine that I was on Fruit Ninja and I had a giant sword. And with my giant sword, I'd go and slice through it. I can't really slice through it in half, but we're going to imagine that I did. And if I did slice through it, the cross section would look like this. Now, my shape is boring and all the cross sections would look the same, but my cross section would look like this rectangle. And when I sliced through it, no matter how great I am, it would have some little bit of thickness. And that little bit of thickness would be the dx part for adding up our integral. So to get the volume of this shape, I'd have the integral of the area of my cross section, too many S's? I don't know, times the thickness. So in this case, the area of my cross section would be the area of this rectangle. So for my thing, my area of the cross section would look like, okay, I really should have a ruler in here. I don't. We're going to fake it. This cross-sectional area for me looks to be about, let's go 5 inches by 3 inches. So here it's pretty boring. My cross-sectional area would be 5 inches by 3 inches. And then my thickness would be a little bit of dx. And I'd be thinking about taking those slices from, we could call that 0 all the way to 9. This would be seriously overcomplicating finding the volume of my box of tissues, but we could do it this way. So 5 by 3, that's 15 dx. So I'd find the antiderivative and get 15x, take that from 0 to 9, and I have 15 times 9, which, fun fact, is exactly what we would get if we just did 5 times 3 times 9. Now, most of the time when we're doing these slices with cross sections, it's because we have a more interesting shape than a, oh, there's a fun name for this, but I've forgotten it. Oh, a parallel pipe end. It's because we have a more interesting shape than just a parallel pipe end. So you could even imagine like my cup here. It has these tapered sides. So if I were doing cross sections this way, then each time I took a slice through, it would be a circle, but they wouldn't all be the same size circle. I'd have like bigger circles at the top and smaller circles at the bottom. If I sliced through my lovely can of red tea that I use to hold my pens, if I sliced through this thing, they'd all be the same size circle. But in general, when we're slicing through, we need the area of whatever that cross section looks like times some sort of thickness.